Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today, we are doing a deep dive into refraction through a prism. It's from Unit 9, Ray Optics and Optical Instruments. We promise a simple, exam-safe explanation that makes this concept crystal clear for you. So let me start with a question for you. Have you ever, after it rains, when the sun comes out, you suddenly see that beautiful rainbow in the sky?
Oh, absolutely. It's just mesmerizing.
It is, isn't it? And you wonder, the sunlight is white, the water droplets are clear, so where do all those colors come from?
Exactly. It seems almost like magic. How does that separation actually happen?
Well, that's the perfect question, and the answer is a bit counterintuitive. That beautiful rainbow, it's created because those millions of tiny water droplets in the air, they're all behaving like tiny little prisms.
Wow, really? So each water drop is acting like a small glass prism.
Precisely. This everyday sight is a massive demonstration of a process called dispersion, the splitting of light. So a prism, which looks like a simple, colorless piece of glass, it has this amazing power to reveal the hidden spectrum inside white light. And that's the magic we're going to uncover today. Okay, so let's start with the core idea. Zero level. What is a prism?
It's that triangular piece of glass, right?
But basically, yes. It's a transparent optical element with two flat refracting surfaces that are at an angle to each other. We call that the prism angle, or A. And when light passes through it, three very important things happen.
Okay, what are those three?
First, there is deviation.
Deviation.
Yeah.
So the light ray just bends from its path.
Exactly, it bends. Second, we see dispersion.
That's the splitting into colors, the spectrum.
Correct. And third, under one very specific condition, we get what is called minimum deviation. And that's very crucial for measurements. To understand the bending, let's use an analogy. Imagine you're walking straight down a corridor. That's your light ray. You enter a room through a door that's at an angle. That's the first surface. Your path has to bend, right?
Yes, I'd have to turn.
Then you walk straight through the room, and you exit through a second door, which is also at an angle, so you have to bend again.
Ah, so there's a double bend.
But
I have a doubt. Why does it have to bend twice? I mean, why is that angle between the two surfaces so important?
that's a great question. Because if you take a flat slab of glass, a rectangular one, light bends when it enters, yes, but then it bends back by the same amount when it leaves. The final ray is parallel to the initial ray.
Oh, right. The effects cancel out in terms of direction.
Exactly. But in a prism, because those two surfaces are angled, the refractions don't cancel, they add up. And this net change in direction is what allows us to separate the colors. Now let's build a mental image of this. Picture that white light entering the glass prism.
I have it.
Inside the glass, the key thing to remember is that the refractive index, N, is not the same for all colors.
So, different colors travel at different speeds inside the glass. You've got it. Red light is slowed down the least, so its refractive index, and red, is a bit lower.
And blue light.
Blue or violet light is slowed down the most, so its refractive index in blue is the highest.
And a higher N means more bending, according to Snell's law.
Absolutely correct. So at both surfaces, blue light bends the most and red light bends the least. And what comes out is not one beam, but a beautiful separated fan of colors. That's dispersion. Now let us see how insert defines this process and the mathematical relations. To do this, we need to know four key angles.
Okay, what are they?
We have the prism angle, A, which is fixed, then the angle of incidence, I, where the light enters. Inside we have two angles of refraction, R1 and R2, and finally the angle of emergence, E, where the light exits. Now, the geometry of the prism connects these angles. Could you please read the relation that connects the internal angles, R1 and R2, to the prism angle, A?
Yes. It says, from the triangle QNR, R1 plus R2 plus AQNR equals 180 degrees. Comparing this with AA plus AQNR equals 180 degrees, we get R1 plus R2 equals A. Perfect. So what that simply means is that the two angles inside the prism always add up to the prism angle A. It's a fixed geometric rule.
Okay, that makes sense.
Now for the total bending, the total deviation, we call it delta, or A. It's just the sum of the bend at the first face and the bend at the second face. Can you read out the formula for the total deviation?
Sure. It says the total deviation is the sum of deviations at the two faces. AIR1 plus ER2, that is AAI plus EA.
Exactly. So the total bend depends only on the angles you can measure outside the prism, I and E, and the prism's own angle, A. It confirms our corridor analogy. Now here's where it gets really interesting. If you change the angle of incidence, I, you'll find that the deviation also changes. But it's not a straight line relationship.
It's not. So what does the graph of deviation versus incidence look like?
It's a curve, actually, a bit like a wide U shape. As you increase I, the deviation first decreases, hits a bottom point, and then starts to increase again. That lowest point, that's the special part. We call it the minimum deviation, or DM.
Why is that one point so important? Why not just use any angle?
We focus on it because at that exact point, the path of the light is perfectly symmetric. The light ray inside the prism travels parallel to its base. And this means the angle of incidence I becomes equal to the angle of emergence E.
Symmetry. And why does that matter for experiments?
Because it's the most stable point for measurement. Any tiny error you make in setting the angle I has the least effect on your result for it. It gives you the most precise value for the refractive index N. So using this symmetric condition, we get the most important formula of this topic. Can you please read the final formula for the refractive index at minimum deviation?
Yes. The refractive index of the prism is N21 equals N2N1 equals sin A plus DM2 sin A2.
And that is the key. In the lab, you just need to know the prism's angle, A, measure the minimum deviation, DM, and you can calculate the refractive index N of the material with very high precision. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROFSAM.com. Let's quickly trace a ray with an example. No heavy calculations, just the steps. Say we have a prism with A equals 60 degrees and N equals 1.5, and we send an array at I equals 50 degrees.
Okay, so the ray is about to hit the first face.
Right. Step 1, apply Snell's law at that first face to find R1, the ray bends inwards. Step 2, use our geometry rule. We know R1 plus R2, which is 60, so we can find R2 easily. That tells us how the ray approaches the second face.
So the first refraction dictates the condition for the second one. They're linked.
Always. Step 3. Apply Snell's law again at the second face, this time going from glass back to air to find the emergence angle, E. Finally, you just use E, I plus EA, to find the total deviation. So it's always Snell's law, then geometry, then Snell's law again. And this whole process is incredibly useful. In labs, instruments called spectrophotometers use this exact principle to analyze chemicals. And in binoculars, prisms are used to fold the light path and make them compact. Now let's talk about the mistakes. Let's tackle 3 silent killers that often confuse students in exams.
Yes, please. What should we avoid?
Okay, silent killer number 1 is about dispersion. The wrong idea is all colors bend by the same amount. Students think this because they forget that N can change.
Right.
The correct idea is that the refractive index in itself is slightly different for each color. It's higher for blue light and lower for red light. So blue light just naturally bends more.
So the key is that N is not a constant for the material. It depends on the color.
Precisely. That's the cause. Okay, silent killer number 2, deviation versus incidence. The wrong idea is thinking. As I increase the incident angle I, the deviation will also just keep increasing.
Assuming a straight line relation, but you said it's a U-shaped curve.
Exactly. But it's a common trap. The correct idea is that the deviation first decreases to a minimum value, diabellium, and then it increases. Remember the hook. Deviation has a minimum. It's a symmetric curve. And the third silent killer is about the mechanism. The wrong idea, which is only half correct, is prisms separate light because different colors have different speeds in glass.
Wait, why is that wrong? We just said they do.
It's not wrong, but it's incomplete. It's the cause, but not the full mechanism. For full marks, you need the next step.
And that is?
The correct idea is the difference in speed leads to a different refractive index, N, for each color. And then Snell's law is the mechanism that converts those different N values into different angles of refraction.
I see. So speed difference causes indifference, and Snell's law uses that N difference to create an angle difference.
Perfect. That's the full chain of logic. All right, let's lock this in with some memory anchors. For the word prism, you can remember. Precise refraction indexes separate light into monochromatic components.
Oh, that's clever. It links everything.
And for a physical gesture, try this. Hold your hands in a V shape. That's your prism angle A.
Okay.
Now take your finger, that's the light ray. As it enters one hand, bend your finger inwards. That's the first refraction. Then as it exits the other hand, bend it outwards again. That double bend in the V shape, that's the essence of it.
I can actually feel the deviation.
And a final thought. Think of Isaac Newton. His prism experiment was revolutionary. It proved that white sunlight wasn't pure. It was a mixture of all the colors. A simple piece of glass changed our understanding of light forever. So let's summarize with 3 final exam-safe points. 1. A prism causes light to deviate or bend at 2 angled surfaces. The total deviation is given by AI plus EA. 2. Dispersion, the splitting of colors, happens because the material's refractive index, n, depends on the wavelength of light. Blue bends most because its n is highest. And 3. The minimum deviation dm is the special symmetric case that allows for the most precise measurement of the refractive index using that formula. Na plus dm2 Sine 2. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROF Sam. Right?
Yes, ProfSam.com. We wish you the very best. Keep that physics crystal clear.